Last time we were talking about bounds. And pretty much anything that you can say about the uh, least upper bound, you can say about the greatest lower bound. And we said a few things before. And I'm not going to give like all the specifics of some of the theorems. They get kind of really tedious, but I think we have the main idea. And let me mention something that we're going to use. Something called the Archimedean property. And the Archimedean property is stated this way. If X is in the real numbers, then there exists and maybe you want to have like a subscript X. You don't really have to do that. It's just more for your own information to say, what this is related to. We can just say N in the naturals. Such that X is less than N of X. So it's actually pretty logical. The Archimedean property says that if you have any real number that you pick, you can always find a natural number bigger than it. Simple as that. So in other words, if you pick any real number, there exists a natural number that's bigger than that. Now, you could also say the other way too as well, though usually this is the way it's actually stated, but you could say it the other way. You could say for any natural number you pick, you could always find a real number bigger. But for some reason, historically, they've always kind of stated it this way. And this is usually sufficient for what we need to do. Now, depending upon your application, or your needs, maybe is a good way to say it. You can state this property this way. If X is a real number, then there exists and like I said, you can put this little subscript X, it's up to you. Some people use it, some just say N in the natural numbers, such that one over X is less than NX, like that. So sometimes it's useful to have that available. Any questions on that? Again, these are pretty obvious things. They're pretty obvious, but sometimes when you start proving things, you need something to refer back to and to have something officially stated. This is almost like what they sometimes call an axiom or a lot of times they'll call this even an axiom, maybe because it's something that's you sort of just take for granted. And so let's look at some problems. And this way up a bit. And so let's take a look at this one. I'm just going to number these. So let S1 be defined as the x's in the reals such that x is greater than or equal to 0. Show that S1 has lower bounds but no upper bound. And then show the inf of S1 is 0. So again, remember the inf is the greatest lower bound. So let's see if we can do this. Solution or now for the first part, show that S1 has lower bounds. And so, of course, you can just pick something. So pick say, and it doesn't have to be this, -5. So since -5 is smaller than any element in the set, it is the lower bound. And now we have to show it has no upper bound. That might be more like, say, we want to maybe call it the proof. So next, show S1 has no upper bound. And again, maybe we want to show this kind of formally. It's, pretty straightforward. And we'll do this by contradiction. And let me put this here. Usually when we do by contradiction, we assume that something is true and proves that we have that says some kind of contradiction. So assume or suppose S1 has an upper bound. Say whatever you want to call it. Let me just give it just some number. Let's call it Q, so that I'm not always using the same letters. And I didn't write that Q very nicely. So you claim out there that there is some upper bound somewhere out there, and that's the value's Q. It could represent, some number, but by Archimedes, by the Archimedean property, we know that there exists an n in the naturals such that n is greater than q, and n is in our set. And like I said, sometimes if you want to give that n a name, you could call it n of q or n1, just to clarify that you're kind of picking a specific one greater than q, but that's up to you. And so we're claiming that q is an upper bound, but we can always find a natural number that's greater than q, and that number and if it's greater than q, and it's also in our set, the way our set's defined. So q is not an upper bound. So we have like a contradiction. Any questions on that? You realize that's a pretty simple proof, but that's kind of the way, that kind of gives you kind of a structure of how you would prove, more complicated things. When you do by contradiction, you prove that you have something, you assume you have this upper bound, and then prove that something doesn't work. Any questions on that? And then also we want to show that the inf of that set is 0. Let me just move this up a little bit here. So the inf of S1 is 0. And once again, we can prove this by contradiction as well. So so we're saying that the inf is 0. Now, first of all, just note that 0 is a lower bound. So it could possibly be an infimum. Remember, the infimum is the greatest lower bound. And so now next we'll suppose that there exists a lower bound let's say W, again, let me just call it W, that's greater than 0. So the only way then that 0 can't be the inf, so it's a lower bound. The only way it couldn't be an infimum is if there was a lower bound that was bigger than it, right? Because by definition, so we'll assume, so suppose there is a lower bound and it's bigger than 0. But again, by Archimedes, we know there exists, again, an N, I don't know if you want to give it a name or call it NW, in the naturals. such that NW is greater than 1 over W. That up a little bit. So the idea is, okay, we assume that there's a lower bound that's bigger than 0. But by Archimedean property, you know, if you take 1 divided by that value, you can always find a natural number greater than that, because this, of course, is like a real number. If you do 1 over W, W itself, of course, is a real number. If you do 1 over W, that's going to be a real number. We can always find a natural number that's bigger than 1 over W. But then if we rewrite this, if we say, and we can rewrite this as W is greater than 1 over NW, we're just cross multiplying. So, and let me just put this up here, just cross multiply. And then, of course, since this is positive, so we can say that this is going to be greater than 0. And now, so we found a 1 over NW, which is greater than 0. So it's in the set and it's less than so W cannot be a lower bound. Therefore, infimum of S1 has to be 0. Just move that. So again, these get a little bit tedious, but you can kind of see, though, what you have to do to prove something formally. So we're trying to prove that the infimum is 0. So first of all, we have to say that it's a lower bound. Clearly, 0 is a lower bound, you know, from the definition of a set. Now, suppose that there exists a lower bound bigger than 0. Then by Archimedean property, like I said, a lot of times, as I mentioned when we did Archimedean, sometimes it's more useful to kind of use this form here, and that's kind of what we did. We know that there's a natural number greater than 1 over W, and then we just cross multiply and get that W is bigger than 1 over that natural number. And of course, that natural number is positive, so it's 1 over the natural number is positive. So we found a natural number that's positive, therefore it's in the set, and it's less than W, so W cannot be a lower bound. And so we sort of picked like an arbitrary number that was greater than 0. So that kind of represents all positive numbers you could possibly pick. And we showed that there would be no positive number that could be a lower bound. Therefore, the infimum of the set has to be 0. Any questions on that? Yeah, it's a little bit tedious to kind of go through it that way, but that's kind of the way you prove something formally. Okay, let's see if there's which ones would be a value here. Lower bound. That one's almost the same. Oh yeah, here's one. We kind of maybe talked about this a little bit before, but let's go through these. Probably good to practice some of these. And get much the same idea, but just gets just a little bit different so that S3 be equal to 1 over n, where n is a natural number. Show that the sup of S3 is 1. And the inf of S3 is greater than or equal to 0. Yeah, and you could actually show that the inf is 0. And we may or may not want to do that. So let's do the proof. So first of all, for this S3, excuse me, 1 is an upper bound. So you can see 1's an upper bound. So remember, if we want to show something in sup, we at some point have to kind of be sure it is an upper bound. So it's an upper bound of the set. And let's see, yeah, so, and then so suppose there exists a W again, whatever you want to call it, less than 1, that is an upper bound. One over 1 is in the set, and 1 over 1 is greater than W, if you really want to make this, is greater than W. So W cannot be an upper bound. Yeah, I guess for this one, we really don't need a formal proof. We just kind of say, suppose there exists a W less than 1 that is an upper bound, but 1 over 1, obviously from this, is in the set, and that's equal 1, so that has to be greater than W, so W cannot be an upper bound. And so anything less than 1 can't be an upper bound, therefore, and we said that 1 was upper bound, therefore, the sup of S3 is equal to 0. And the next part, let's see if I can do the next part without messing it up. And so here, So the next part show that the, yes, sir.
Was the soup supposed to be equal to 1?
Oh, yeah, thank you. Yeah, thanks. Therefore, the soup is equal to 1. Okay. Yeah, thank you very much. Okay, let me try the next part. And see if I can not mess that one up. So now I want to show that the inf is greater than or equal to 0. So and so this one we can probably show this directly. We can probably just say for all n in the natural numbers, 1 over n is greater than 0. So the inf of S3 has to be greater than 0. Greater than or equal. Yeah, probably that's enough right there. So since everything in the set is greater than 0, maybe I should say the inf certainly has to be greater than 0 for all n natural numbers. 1 over n has to be greater than 0. So everything in the set has to be greater than 0. And
that doesn't mean that if it's greater than 0, does it?
Yeah, right. I get, yeah, right. Yeah. So I guess that's enough to prove it right there. That's right. So it really just that pretty much just says that the inf is greater than or equal to 0. Yep. Yeah, I guess that's right. It right there. Yeah, I guess that's all there is. I guess I was trying to make more of this one than necessary. Yeah, I think that's it.
So I was wondering, so for like the first part where we're trying to prove that we're trying to prove that the soup is 1, right? If we have that 1 is an upper bound, and also we know that 1 is in the set, we can say that 1 is the maximum, right?
Yes.
And so is it okay? This is like all maximums are also soups, right?
Right.
So could we just say that and that be our proof? Is that legitimate?
Yes, yes. So that's right. You could do that. Yeah, you could argue it that way. Yeah, that's a good point. In fact, let me write out what Ben's saying. Yeah, that'd be another way to prove that as well. So for number 3, for the soup S3 is equal to 1. We could also say argue or proof, how do I say it? We could also argue that 1 is an upper bound of S3, and since 1 is in S3, one must be the max therefore, the sup of S3 is gonna be 1. Like Ben's saying, if you have a max, then that has to be the sup because that's in the set. And so anything lower, smaller than something in the set has to be smaller than that max. Yeah, good. Yeah, you could definitely argue it that way as well. Any other questions on that? Okay, let me try this next one and to see if we can work through this one. And this is number 5. Let S be a non-empty subset of R. Find it below. Prove that the inf of S, and we'll call that's like a capital S, is equal to minus the sup of negative S, such that S is in the capital S. So let's see if we can do this one. So first of all, we're told S is a non-empty set, non-empty subset of R is bounded below, and prove that the inf of S is equal to the negative of the sup of the negative values of S in the set. So again, this set here consists of all the values in S, all the elements in S with a negative in front of them. So let's see if we can do this. So since S is bounded below, there exists a capital M that's smaller than, less or equal to S for all the S's in the big set S. So again, since it's bounded below, we have that there is, some lower bound, some infimum, that's true. So let's say the infimum of S is less than or equal to S for all S in the set. So all we're saying here, it's bounded below, there's lower bound. So if it has lower bound, it has an infimum. And so there exists an S star in S such that S star minus epsilon is less than that infimum. So all we're saying here is, again, has infimum, just like we said before, if you go, if you go, like, say, a little bit below, you can always find something in the set such that if you take a tiny bit away from it, you can get below the infimum. So and then let's see, or excuse me, yeah, there exists something in the set S such that S star minus epsilon is less than the infimum for all epsilon greater than 0. And I just want to be sure that makes sense. If we have an infimum, it's less than or equal to all values of S. And so now what this is saying, and this is kind of important, so that if you pick an epsilon, so let me sort of write this out. If you pick an epsilon, you can find an S star in S such that S star minus epsilon is less than the infimum. That's just kind of like want to make it clear. So there exists, so this is going to be, so you pick an epsilon, no matter how small it is, you can find an S star in the set such if you take that epsilon away from the S star, you can get less than the infimum for all epsilon. So the idea, you might even, so I kind of want to state it this way, because sometimes you may even want to state it the other way. You can say for all epsilon greater than 0, there exists this, might be a little bit clearer way to say it. Any questions so far? Because I just want to make it clear what we're saying with that. Okay, so now, let's go to the next one. Let's say, so, and we maybe want to make this in 2 parts here. And so let me write this over here. So the infimum of S is less than or equal to S, of course, for all S in the set. That's by the definition of the infimum. So multiply by -2. This should be -1. And then we're going to end up having that the negative of the infimum of S is greater than or equal to minus S. For all S in S. So the infimum, let me write it this way. So negative the infimum of S is an upper bound of this set minus S, S in S. Like this. And so now, let's go maybe over here. As we said, for all epsilon greater than 0, there exists an S star in S such that S star minus epsilon less than the inf of S. And then once again, multiply by -1. And we'll end up with negative S star plus epsilon is greater than negative the infimum of S. And once again, that'll be for all epsilon greater than 0. So negative infimum of S is the least upper bound it's the least to me yeah, it's the least upper bound of the set negative S such that S is in S. So putting that together, the inf of S is equal to the sup of negative S. S is in S. So the inf, so that if we multiply by -1, the inf of S, sorry, is equal to negative of the sup, negative S. S is in S, like that.